Hello there, I'm the Biz Manager and welcome to a tutorial where we are going to build step by step one of these bad boys, my friends. So I have showcased different designs over a few videos. However, these things are very complicated just for me to show you. So what I'm gonna do is I'm gonna delete all of this and we are gonna build one part at a time, and I'm gonna do my best to explain why every single thing exists over here. Alright, now we have a little bit of space over here. So pretty much, what's the idea? The idea is to have a single ribbon going throughout all of our map and have multiple systems connected to it. These systems will encode a signal into the ribbon, which is then going to be decoded later on. Now, how are we going to achieve this? Let's try and come up like if I was like doing this from the beginning. So first we need a way to generate a frequency, right? That's the easier part. We can either go like this with a cycle sensor, all right, or we can go like this with one NOT gate bridged, just like this. Oh, this is not the one that I want. Okay, that's totally fine. Get out of here. It's this one, timer sensor. Timer sensor, come here. There we go. The timer sensor we would put to 0.1. Get out of here, message. 0.1. There we go. So, if we unpause and go into this menu, we can see that this thing is pulsing, right? That's what we want. Now, we want a way to count those pulses. All right. Where is you? There we go. Now, luckily for us, we have these beautiful things, the signal counters. These things are going to be mighty helpful to our cause, because, yeah, these things allow you to count signals, and whenever a set amount of signals is reached, they will send a green signal, and then whenever another signal is sent after, you know, the count has been reached, it's going to self-reset back to 0. Okay, cool. So, what next? What next? Oh, wait. Because we can't just have this thing counting, we need to write as well. But this is gonna start being a little bit more complicated. So, let's think about this. So, we will have a frequency being counted over here. However, we can't connect this directly because we need a way to control it. If we just go like this, all the things will be counting at the same time. So, what we can do, we can use AND gates. These things will be your best friend, because an AND gate will allow you to pretty much, this will work as a switch if this signal will be allowed to pass through or not. Okay, so given that we have these AND gates over here, we'll have to connect the frequency generator to one side, and the other side must be controlled by something else, something that is going to allow us to open the AND gate. Okay, so let's say this wire over here will connect, it can connect to the first pin, why not, and then we need to go like this, then like this, bam, that way the first pin will be connected to the frequency generator, which means this one will be like the turn on and off switch, shall we say. For that, we are going to use memories, because memories are very useful. Even just a pulse will... Oh, man. I'm not going to be able to unsee this. I'm sorry, my friends. I have to switch this around. Okay, much better now. Otherwise, my internal OCD would go crazy. Okay, in any case, we need a way to turn on and off the AND gates. We can use memory toggles for that, because memory toggles are very useful in the sense that a single pulse will be turned into a constant green, which is something that we want actually, because with this in AND, right, we can kind of control the amount of time that this will be open or closed if we send a signal into the reset thingy over here. But oh well, that's all for the future. And then, you know, we need a way to activate this signal. So far, very simple, right? Right. Yeah, okay, so we have the switch on and off to turn on the counter thingy already done. The frequency will come from one side, the signal will be turned in the other. So this thing will start counting. The second it receives a green signal on the turn on and off side, because the other one is constantly going off, but it can pass through until this one is green. So that much is solved. Now, how are we going to write into the line this signal? Well, we can either have each counter write into have its own writing device, shall we say, into the line, or because only one of them is active at the same time, we can bridge them all together. That way we save on space and materials, and truth be told, we only need one writing mechanism to write all of these things. So yeah, we can bridge, for example, the first digit, all of them together. So let's take care of that. Let's bridge the first digits. Like so. And then we bridge the second digits. Like so. There we go. So, technically speaking, all the digits are kinda, connected to each other, but once again, only one of them will be active at a time, so they will never interfere with the others. Not only that, because this line is broken, the signal will not drive backwards, causing problems. Okay, so this will start to count these pulses. Okay, and whenever a code is reached, so for example, my favorite 57, right, a staple of every automation system. Whenever 57, in this case, 5 pulses are sent in the one digit, or 7 pulses are sent in the other, this thing is going to send a green signal. However, like I said, it's going to count over again, so we need to memorize that signal, right? Here comes the trusty memories again. Let's give it a little bit of space because we might need some. So there we go. Whenever this counts 5, it's going to send a green signal, which immediately is going to turn red, but hey, a green pulse is all that it takes to activate this thing. So, cool. Alright. This will remember the number has been reached. Alright. We are almost there. We are almost there. From here, we need to send into another mechanism somewhere. Because, this by itself doesn't... Oh, man... This by itself does not turn off anything, does it? But wait, what have you said about turning on and off again? Oh yeah, AND gates very useful, ain't they? But this thing is gonna be sending a red signal, so it's not going to turn on the gate whenever it is necessary. So what we actually need is another set of memories, which are gonna be resetted by these memories over here. So, with that in mind, we now know that we need a one AND gate to serve as quote-unquote a switch, right? And we can open that switch with the memories, just like we did over here. Something like this. And then these switches can be turned off by these memories over here. So we go like this, we go like this, and we go like this. Cool, all right. So we are one step closer, but how are we going to activate these things? Yeah. Oh, I know. You see, once again, we are talking about switches and activation of things. Nothing that an AND gate cannot solve for us. I think it's, yeah, the AND gates, they are fantastic. So we're gonna put, let's say, not over here, don't be stupid. Don't be stupid. Or maybe we can be stupid. Yeah, that's not a terrible spot. Let's relocate our frequency generator to a more convenient spot, like for example over here, maybe over here, so it's not in the way of anything. Okay, so in here we have the frequency generator going crazy. Something is going to activate this AND gate in the future, and of course that I deleted because I'm a dum-dum. Okay, in any case, this is going to activate the AND gate. Something is going to activate this AND gate in the future, and this AND gate itself is going to travel into two spots over here for this already previously constructed thing, and then it's going to go over here to write into the bit, right? We are almost next to the bit. From this AND gate, we go straight into a bit writer, like so and like so. So we are just one step away from writing into that line. We go over here and we connect like so. And then we go over here and we go like so. Just for experimental purposes, right? I'm just gonna put that over there. So if we were receiving a green signal, as we can see, the signal would be able to go over here. But how would it activate this? Well, quite simple. Like I said, this thing only needs a pulse to activate. And this line is filled with pulses, you know, it's having an epileptic seizure or something. So, yeah, there we go. See, a single bit, it's all that it takes to activate this thing. And it is not going to care, because, you know, if the activation line is dancing, it's making some breakdance moves or whatever, it's not going to care. It's gonna stay stable. And the frequency will then be able to pass into the bit writer. Cool. So, whenever this thing activates, it's going to reset these lines, which in turn are going to close the gate, which is going to stop the signal from being written into the bit. Would you look at that? We are almost done. Not really, but almost there. So we have figured out the first part of this entire thing. The writing mechanism, shall we say. However, we still are not exactly anywhere close to stopping it, because, you know, even if this stop over here, right, these things would in theory still be green. This is where the 4 ribbon thingy comes into fruition, because eventually we're gonna need to receive a confirmation that our message was received, and that confirmation, it's what is going to pretty much reset everything in our encoder. This being one of those things. So we already know that we are going to need some bridges over here, so let's just build them, because you know, I have a tendency of being disorganized, and that's probably something that we should take into consideration, right? We're going to need the line over there. So that's something for a little bit into the future, right? We're talking about confirmation, end of message bits. We are not even close into writing a message, let alone receiving a confirmation. So let's continue delving deeper into this encoder. Okay, so let's take care of this mechanism over here, because you're not going to be manually switching on and off your encoder, right? You're making an encoder, you want it to be automated. So let's say we are going to receive a signal from somewhere, right? It doesn't really matter where, it's a signal. We need a way to make that signal go all the way over here and activate this AND gate without causing too much issues. So let's say it's going to flicker, right? Let's say your automation might flicker, that would interfere with the message. You need the message to be completely written whenever everything is enabled. Therefore, you need this thing to be stable. So you're gonna need one of these. All right. Can you please? Thank you. There we go. You're gonna need one of these. Alright, so sounds easy enough, okay. I mean, even the confirmation bit would be able to reset this, and it would be nice. However, if you're gonna have multiple encoders, you'll need a way to keep that message waiting, right? So we're gonna need something else. Okay. So we're gonna need another switch of sorts. A switch that allows me to turn it on and off whenever I have a message being written or not. Okay, so switches, you say. Where have I heard that before? Whenever we were speaking about AND gates. Yeah, that's right, my friends. So we are going to need an AND gate. So if you're going to need an AND gate and this might flicker, that means I need another memory before that. All right, okay. So another memory before this AND gate, and this AND gate will be the one that activates the thingy or not. So in here, how are we going to proceed? Let's think about it for a moment, shall we? So we have a line over here. We need to distinguish which bit does what. We are going to write into bit 1 and 2, which are going to be our digits. We also need 2 additional systems. We need the confirmation system, and we need the line busy system. Other than that, we don't need anything else, at least from this line itself. So, at least for me, the way I use this is 1 and 2 code. Really, I'm not paused. I should be paused. I should be paused. I don't want my test dupes being doing like nothing. Just, whatever. Bit 1 and 2, right? Message. The way that I do things. And then bit 3, line busy. Bit 4, confirmation bit. So, over here, right, we would have the bit 3 thingy. The confirmation message. So we need a way to send a message and to receive a message from the same bit. And in a way that we can like interpret that our encoder needs to interpret, like if I'm sending a message and I'm receiving a message at the same time, that can only means that I'm the one writing. Okay, with that logic, we can then look at the parts that we have available to us, loud motorcycle, and see what could possibly work like that. Well, we have kinda the XOR gate over here. The XOR gate doesn't exactly work like that, but it kinda works like that. So, we could put one of these, come on, which would be reading the line going into the bit 3, and then would be reading also the bit 3 itself. Okay, there we go. So let's go over here, bit 3. So how does the XOR gate works? It only sends a green signal should one of the lines be green. If both are green or both are red, it's going to send a red signal. However, that's precisely kind of what we want. We want this thing to say that it is okay to write if both are red, meaning no one is writing, or if both are green, because that means the line is occupied by me. And so, we only need to reverse the XOR gate with a NOT gate. Perfect! We have our signal. Beautiful! Alright! Let's go like this. Perfect! So now we know no one is writing into the line, this AND gate will be active, and whenever we receive a message from the waiting memory over here, it's going to be allowed to go through. However, if a message is being written, it's this encoder will just wait. You know, the message will get stuck in here. It will not be allowed to advance until this line over here, or until both of them are read. Okay, we are one step closer now. Can I connect this directly? Kinda, because do you really want this line to be permanently green? Let's say your message is sent and this is permanently green. You know what's going to happen? Your message is going to be sent again and again and again and again. You don't want that, because the encoder, it's a busy person. It needs to talk to other people. So you need to pulse your signal. You need to turn this analog into a tiny little pulse. The way we do that is quite simply with another memory, like this, and then a filter gate, like this. Now, depending on the time of your pulse, you pretty much set up the filter. Usually, I go for 0.1, because that's all that it's needed. You connect it like this, and then you connect it like this. This pretty much means that this thing is going to self-reset itself after 0.1 seconds. However, that 0.1 seconds is all that we need to activate this thing. So, cool. All right. One step closer to our objective. So, in theory, if we go like... Hello, beautiful. If we go like this, right, and if we activate it, the pulse will be able to travel through here and end up, you know, eventually being written over here. Okay. So, this is what I like to call the spine of the encoder, my friends. Every encoder, regardless of design, has a spine just like this. So if you want to make a single encoder, a super encoder, or an infinite encoder, this part remains always the same, and this part always the same as well. The difference is what we are going to discuss next, because, alright, we have our spine kind of figured. There is a few things here and there, but we'll address them eventually, whenever we are trying to iron out the wrinkles. But right now, we have a bigger problem, because, well, it's all fun and games, but these memories still are not going to reset themselves. Are they? Something needs to reset them. But what could it be? Well, there is two ways of doing this. You can either reset all of your memories through the pin 4 confirmation bit, or you can have an internal self-reset mechanism, which is something that I advise should the message get lost in travel because the game had a brain moment. Okay, it happens from time to time, it's oxygen not included. So if you don't receive a confirmation bit, everything is gonna get stuck at green, and that's going to stuck your encoder. So at least, even if the message is lost, if the encoder can kinda... Oh my god, really? I'm sorry, my friends, I live in a very noisy neighborhood. In any case, so if the message, the pin 4, is not received, everything is gonna get stuck. So you kind of want to have a little bit of a safety going on. How do we do that? Okay, let's think about it for a moment, shall we? We need to kind of know whenever our message is fully sent. So we need these two things to be green at the same time in order to kind of know that the message was at least sent, not received, but sent, right? So what we can do is use an AND gate for its, actual purpose, other than just being a switch. Wrong position, please, go away. Actually, than just being a switch, it's going to be an AND gate for once. So whenever both signals are green, that means the message was fully sent, which means that in theory at least, it is time to reset. So we can do something like this. We go through here with this wire thingy, and we create what I like to call the reset pulse. So what is the reset pulse gonna do? Well, like the name says, it's gonna reset pretty much everything. Like, let's just... that's poorly positioned, good sir. Sure, it can be like over there. Please, game, thank you. So, the reset pulse, what could possibly do? Well, other than the name itself, if the name is not obvious enough, it's going to reset the entire thing. So what needs to be reset in this thing? Well, we need to reset this thing, right? We need to reset the counter, because, you know, you don't want to have this thing stuck, like, after the message is done, it's going to be like at 21, for example, right? And you want it to be sent back to 0 whenever the time comes to write another message. So this is what that is going to do. From here, this message will also travel to all the other memories that need to be resetted after the message has been written, which are these two, and then all of these memories over here as well. So perfect. Would you look at that? It even fits in place. Beautiful. All right. There we go. So yeah, our encoder is now capable of self-resetting. And you know what? It is time to hydrate myself a little bit. Okay, so we now have the basic mechanisms of a single encoder, but we have a multiple encoder over here. We need a way to make it write more than one signal, because yeah, we have multiple things over here. What's going on? Well, in here we are going to make a way to have the system select individual channels one at a time, because we can't have multiple channels written open at the same time. If this is 57 and this one is 61, well, which one comes first will close the gate, and so the other message will not be sent. So we need to wait a little bit. Okay. How are we gonna do that? Let's think about it for a moment, shall we? So, we need a way to keep one channel open at a time. So, what could we do to do that? Well, I have come up with, I like to call, a self-powered perpetual automation machine. Inspired by real-life perpetual machines that don't exist, but are still a cool concept. The idea is to have a memory that is open, but whenever the time comes to close, we'll activate the next memory right next to it, and whenever this one comes the time to close, we'll activate the next one, and then the next one. How are we going to achieve this? Quite simple, my friends. Okay. Maybe I'm a little bit too close over here. Maybe I need a bit more space. Because this is a big boy, okay? This one is gonna be a big boy. let's just go like this, and like this. I mean, I built all, I cleaned all this space, and I'm almost done. So how about I just use it? Let's take care of the self-powered perpetual machine over here somewhere. Like for example, over here. So, like I said, memories that activate the next memory right next to it whenever the time comes to turn itself off. So, we already know how to turn off a memory, right? We go through a filler gate that self-resets its, self-resets itself. It doesn't sound super correct. But well, let's not mold over it. So, yeah, you need a way to kind of... man, I'm trying to position this in the best possible spot. Let me just shit for a little bit. Let me take a look at my notes. Okay, it doesn't... makes more sense like that. Alright. Yeah, we need a way to pretty much have this gate activate this filter after a certain amount of time has passed, which in turn is going to activate the next one and reset itself. So you can either, like, for example, go like this. Alright. This is probably a cheaper method, because the one I am using currently actually has two these things, but it's for compacting reasons. In here we don't need to worry ourselves with compacting these things. So yeah, should this thing get activated, right, it's gonna send a green signal through here. However, it's gonna wait for a set amount of time until this pole over here becomes green. Whenever that happens, it's going to reset this one and activate this one, which means then this is going to be green, send a green signal through here, which will only go through this part whenever that time has elapsed. And then over here the same, and then in the next one the same. And by the way, my friend, I'm sorry if I'm being so extensive and redundant, but this is a little bit complicated, shall we say, even for me to understand. So I'm doing my best to just try to leave this thing as unambiguous as possible. Okay, so yeah, and there we go. This is now, in theory, a self-powered perpetual machine. So let's activate it, shall we? Right now everything is red. The second we build this, let me just deconstruct this now. There we go. It is going to keep the signal in motion, you see? Like, it waits, and then goes into the next one, and then the next one, and then the next one. And yeah, with this technology, you are not limited to 4 channels, you are limited to how many channels you can fit in your map, pretty much. How much space do you have? That's how many channels you can have. Okay, so, channel part, done. We can't just have this thing going like willy-nilly, right? It needs something else, because we can't have this perpetual signal activate the encoder, right? That doesn't make sense. Otherwise, we would be sending this signal like at regular intervals, and that's not what we want. We want this to be activated. Something like a switch. Oh, there we go again with the switches. Alright, Base Manager. Enough with your switching shenanigans. How about we get rolling with this? So, yeah, this is why I built it the way I built it. Because I need the space to have the thing going. Okay, it makes sense now, I'm remembering. So yeah, even though this is a self-powered perpetual machine, if we want to fit everything in place, we are gonna need to do a few gymnastics, shall we say. So, let me just deconstruct this and rebuild this as it should be. So, let me just look at my notes, because this is kind of thing that I spend hours thinking about. So yeah, it's not like I can just replicate it off of my memory, because even though you might think, oh, Base Manager, you have to be super smart to build something like... No. You don't need to be super smart. You just need to spend enough time staring at something until it makes sense. So yeah, the smartness not my forte, but in any case. So with all of that said, let's just replicate what I have already done in the past. Let's not try to reinvent the wheel, because it's not gonna work. man, come on, rotate that thing. Yeah, this is what we need. And it's gonna make sense in just a moment. Okay, so pretty much instead of having one, we need to have two. How is this better? I wonder, right? It is, trust me. We connect it like so, from here all the way down, right? This one resets, and this one receives the signal from this one. So this one goes like this, all right? And then like this, and then like this, and then we replicate it all the way into the end, just like this, all right? And then we can bring the signal through here. Why did we build this like this? Well, because now, my friends, we can bridge our activation signal through the middle of our self-powered perpetual automation machine. There we go, and then we go like this, like this, like this. This one doesn't need to be like bridged, but you know, it's one of those things. You need space to build other things, so having more gates is actually more organized. Alright, so now that we have our self-powered perpetual machines and we have our activation end gates, the only thing we need to do is have a memory to take care of the flickering, so that the signal doesn't like flicker while, you know, we are trying to have a message being sent. We kind of want to remember things over here, so like memory for remembering purposes. Man, this is gonna be a bit more confusing than I thought, but well, confusing in the wire sense, because guess what? This will also need to be resetted eventually, right? So if you were thinking about the self-resetting line or the pin 4, you would be correct. This one is up to you. You can reset this with pin 4 or with internal self-reset. Doesn't really matter too much. In fact, none of them actually matter too much except for these two. Yeah, you know, so these ones are the important ones, but in any case. So we have the memory. This memory gets activated by the thing that, you know, by your switch. You could build this like this and it would work. Now, an additional piece of safety, safety for your system. Because here's the thing, let's say that you have an Atmos sensor that is requesting oxygen, for example, and for some reason the message got lost. The way this works will mean that even though the message got lost, the encoder will self-reset itself, meaning it's going to go back to square zero. If, you know, this is continuously sending, like, it's, if this is continuously sending another green signal, that means that this is gonna work again and again and again. Like, we don't want these kinds of things to happen. We don't want to have encoder overloaded by a single message that is simply stuck. So what we can do is we can do something very, very simple. We can make another memory toggle. However, this memory toggle will go through a buffer gate instead of a filler gate, okay? And these buffer gates, okay, you go like this. Wait, let's not connect it just yet, because things will go into motion and we don't want that. But instead of going like this with the fillers, you have with the buffer. Why do you have a buffer? Because if you send a green signal, I'm going to cut it over here so that you guys can see it. If we send a green signal over here, what will happen is that this thing is going to briefly pulse. There we go. And then the buffer is going to wait for 5 seconds. And then it's going to pulse again for 5 more seconds and then pulse again. Which means that you can pretty much crank this all the way to 200 and then have a way to simply remind your network that something is still waiting. Like if once again, if the message was lost, for example, oxygen was requested, because oxygen didn't arrive, the Atmos sensor didn't went into the reds, which means the signal is still green, and therefore it needs a little reminder in a little while. Okay, you need to give time for the system to act, right? The oxygen probably will come from the other side of the map, so you need a little bit of time for things to roll into place, and therefore you kind of want to crank this all the way to 200 seconds so that the system is a little bit more patient with its constant signal sending, right? It's like those kids in road trips. Are we there yet? Are we there yet? Are we there yet? If you could space the "are we there yet" every 200 seconds, would probably not be as annoying as it is, right? Cool. Okay, so we are one step closer to getting this thing done. And by the way, if the signal goes red, then this buffer, after the time has elapsed, will simply go into red and into resting mode, right? So yeah, this is actually almost done. Because now we have two things that are not talking to each other. We have the main spine of the encoder right here, and then we have the channel switching part of the encoder, which is right here. If a message would be sent right now, it would go over here, wait for this thing, and then be stuck over here, right? Because this AND gate is closed right now, because this thing is also closed. Therefore, we need a way to let the spine know that a signal is being written, and this is where the lack of space is going to be a bit annoying, but well, we'll work around it. That's totally okay. Not an issue whatsoever. So what do we do? Pretty much, if the signal reaches this stage over here, it means we are in business. Therefore, we kind of want to splice all of these wires together without having them communicate with each other, so to speak. Because if this wire, if we go like this, like for example, if we go like this, like we did in here, that is not going to work, because this is going to go through here and activate all the memories. Yeah, we don't want that. That is disgusting. So we need a way to have the wires all spliced up, but not connected to each other. So we are going to go and we are going to use OR gates. Beautiful, beautiful OR gates. We go like this, like we only need this. We don't need the middle one, because this wire is already going to be connected to an OR gate. So we go like this, like this, like this, and every like 2 wires you put an OR gate in, and then you bring it down, and this wire can be bridged together because it's separated, and therefore it's not going to travel backwards and activate things it shouldn't. So this is our main activation signal. So even though like there is ways to build this a little bit more organized, my friends, well, I'm doing my best to explain this, so I'm not thinking too much of the Tetris of this thing. So yeah, this is the main activation signal. It's going to go there, and it connects into the bottom of our spine over here. And should a signal go through here, it's going to activate this OR gate, which is then going to send this signal, which is then going to activate this pulse generator, which is then going to send its message to the memory of waiting, the waiting memory, which is then only going to send its message should nothing be written over here, which is then going to activate this AND gate, which is going to tell, hey, I'm writing, and at the same time activating the AND gate for the frequency generator, which is then in turn going to send the frequency generator into these AND gates, of which only one should be active from these memories over here. And then the message is going to be written over here. Once the message is, once the amount of pulses have been reached, these memories over here are going to activate, deactivating these over here, which have been previously activated by the pulse signal itself. I think that explains it. Now, little details. This thing works pretty well. However, if you are unfortunate enough to have 2 encoders go off like this at the same time, you are kind of in a bad mood. It can happen. The game is truly like that. So what do we do in order to prevent such a terrible event from happening? Well, we use our old trusty friend, the filter gate. The filter gate is gonna be your best friend when it comes to these things. So in this filter gate over here, what you're gonna do is set up priorities. An encoder which has high priority, you will give it minimal time. One that has like low priority, you can give it like 2 seconds. That should like keep the things so out of phase with each other that you should never be unlucky enough to have 2 encoders activated at the same time. However, of course, if this one activates 1.5 seconds before the other one, it's going to be a bad day anyway. So yeah, the game still have ways of trolling you. Don't worry, the game will find a way. But at least with this, we can kind of prevent it from happening in the first place. So yeah, that's one of the safety systems that we could put into place. More things, for example, let me think. Oh yeah, we haven't finished like the CAN bus. No, we only have the encoder over here. we only have the encoder, so we are only writing into the first pin, into the second pin, and into the third pin. We still have one more pin, right? We talked about confirmation, didn't we? Of course we did. We need confirmation from pin 4 itself. So, where is this gonna come? Let's take care of building a decoder and then testing this thing and see if it actually works or not. Because if it's not going to work, we will then go through the steps of troubleshooting. But I think it's gonna work. Now, decoding time. How to build a decoder. Step 1. Where are you? Build the signal counters. Pointing downwards. Or upwards. It doesn't matter. Now, you are gonna need at least, okay, let's start with, let's say, 2 signals, right? Signal for pin 1 and signal for pin 2. Right? So this will go over here and this one goes over here. Pretty simple. 50. 7. Come on. Alright. Now, because 58 is technically 1 above 57, and that means this is gonna count 57, it's technically for a split second gonna send a green signal. We don't want that now, do we? So in order to prevent ghost signals, we are gonna have filler gates set to 0.5. That's all that it takes. You don't need 5 seconds. That would be too much. 0.5 seconds is all that it takes to get the ghost signal out of this. So we connect this into these filter gates, and then we need to have an AND gate to combine these things together. No. Before the AND gate, we need our old trusty buddy, the memory toggle, because yeah, this thing is gonna count to 57, but it's going to be so fast that you kinda need to have the signal memorized for even if it is just half a second. Yeah, it needs to be memorized, otherwise the thing is not going to work properly. So you need to stabilize this signal for a split second, so we are going to use memories, and from the memories we combine both of them, because for example 52 is going to activate the 5, which is going to activate this one, which is going to send the green signal over here, but because we have an AND gate, this one is still red, nothing is going to go through, so no problem there. We need the precise code for the signal to be able to pass from this point onward, so we go like this. Okay, cool. So, both are green. We now are 100% sure that this was meant to be activated. Okay, so, because, like, for example, we want to have a constant thing happen, right? We don't want, like, nothing bad, or in this case, we don't want the system that we want to activate to forget that we want to activate it. So, memory time. Yeah, this is the final memory. This is the thing that finally turns the code back into a stable signal. The same that would be sent from, for example, from here, right? But it's now being sent from over here, from this memory. This is going to activate whatever you want to activate, like, you know, build one of these. It's for testing purposes, right? This is what gets activated. By the way, give me power. Give me power, please. Thank you. Power for the masses. But this is still not done, are we? We will have a code, which means we need to reset this, and then these memories will also need to be reset. This is different. So how are we going to reset everything? Now, everything needs to be resetted. The code has been sent. It has been received. How do we reset all of this? We have so much. That's where pin 4 comes into fruition, my friends, because this message doesn't go only over here. It will then go into the side. And let me think. Okay, this goes into the side and then needs to be probably buffered for a little bit. Because even though I have one right next to me, I don't want to go over there and look at it. I can figure this one out, I'm certain. I built this once or twice. So yeah, this needs to be buffered for a little bit, because if we are going to reset the entire signal, we kind of want the pulse 4 to be not exactly a pulse, but like a signal that lasts 0.5 seconds at least, you know, so that everything has enough time to reset itself. And oh, don't look at it. It's right there. We need to be zoomed in. No, I'm joking. I'm at a loss. What I need to do? Oh yeah, I need to generate a pulse. Dummy. This would also work, but probably not as good. Yeah. Okay. I stand corrected. Past me was right. We need a pulse. We do need a pulse. It's not going to work otherwise. I can fit it in here. So let me just go like this and then like this. Okay, this pulse is going to be slightly different. Like I said, we need this to be open for a little bit longer than all of our other pulses. So this one we are going to keep at 0.5. We kind of want to make sure that the system is the reset system is active for a little bit of time so that the message is received by pretty much everything. Okay, so from here we can write it into pin 4, the confirmation pin. Okay, we are one step closer now, one step closer. So we send the pin 4, but is this going to reset this? No, we can't have a self-reset decoder like we have the encoder. And the reason for that is quite simple. If you have multiple encoders, they will always be reading from the line constantly. However, they will only send a green signal whenever the precise code is sent. Therefore, you need to reset all of your decoders whenever a pin 4 message is sent. So that's precisely what we are going to do. We are going to read from the line. Come on, over here. We're going to read from the line, from the pin 4. Every time a bit is sent, it's going to go through a filler buffer setup. The reason for that, we kind of want this to be a little bit stable. Once again, it's for stabilization purposes. You can have the wire connected directly to the things. However, because the game likes to have brain farts from time to time, message will be lost. So yeah, do this. Okay, buffer, you want to set the buffer for 0.5 and the filler to 0.2. That's all that it takes. Okay, that's all that it takes. A 0.3 second message will be more than enough to reset this and then reset the other one over here. Bam! And I think everything is resetted now. Now, this over here, this is the memory that activates the system. This one needs to be resetted by other things, okay? You can either have, for example, 2 decoders, one with a activation code and one with a deactivation code, or you can have what I like to call the turn on and off decoder, which means if you receive a message, it turns on. If you receive the same message again, it turns off. That's achieved by pretty much... I don't have space. I'll have to just rebuild this thingy over here. Just one quick second. We just need a tad little bit of space to build the extra infrastructure. Alright, so over here, perfect. Okay, so pretty much what you do is you have this signal go in here to activate, and then in order to reset this, you send it into a counter thingy. Counter, where are you? I'm blind sometimes. You go in here into a counting signal counter, and the signal counter is going to be set to 2, because the way this works is, let's just mimic a green signal, shall we? 1 means active, 2 means deactivated, and now you say, but why not just count to 1 0 1 0? Because this thing goes back to 1 after that. You can have it go back to 0 with advanced mode, I think. Yeah. But yeah, it's one of those things. You either have advanced mode with 1 or normal mode with 2. Okay, so pretty much it's just going to activate every time, deactivate and deactivate every time it receives 2 pulses. Okay, cool. There we go. So now you can have the same signal activate and deactivate a system over here. So now let's try to do just that. Let's try to go through all of this and see what happens over here. So let's connect all the final bits and bobs. This thing is active because I demonstrated the thingy previously, but that's fine. It will reset itself. This one can be activated. It's fine. It doesn't matter too much, at least for now. I think everything is in place. If it is not, we will find it pretty soon. So let's go. Let's pause the game because we want to see this in action. Now, I won't be able to explain too much, okay? Because this thing happens pretty quick. So let's see. This should go over here, which should only be... Oh, I need to activate the self-perpetual. thingy as well. So let's just go like this and like this. So this is now active, as we can see. Whenever the code starts being written, I cannot pause the game, because if I start spamming pause, the game will freak out with this active. So yeah, as we can see, the signal is going. It activated this thing, it activated this thing, and activated this thing. Then the signal travels backwards, and it's in the process of activating the spine. This is set to 57, right? This is 57, this is 57. So let's go. Let's let the system do its thing. Okay, it almost worked. Oh no, it did work. It's just that the timers are not exactly super great, but yeah, it did work. It did work. We just have some timing issues, like for example this one that I was almost certain I had set up to 0.5. Almost certain, but not totally certain. But yeah, I think that's the only issue we faced. Everything is actually already set up properly. Alright, now over here, what do we have causing us issues? Why is this set up to 1-1 and not 0-0? Oh, because I'm a dum-dum and I did not connect everything over here because I am a oh my god. Base manager, connect your wires. Connect your wires now. The great thing about this is that you can purge any errors from your system by utilizing a bit 4 with one of these bad boys. You just stick one of these in your base somewhere. And this, I think I screwed up something over here. In any case, disregard that. It's just my fat fingers going all over the place where they shouldn't. Oh boy. So yeah, if you send a signal through bit 4, that's going to pretty much purge the entire system out of all of its important errors. So let's go like this again, and let's try again, shall we? 200 seconds, it's too much for me to wait. Send another signal, please. There we go. So another signal was sent. And oh my god, base manager. It is kinda important to kinda, you know, rebuild the wire after you deconstruct it, but well. Let's see if this works better now. It did. Much better. Why are you still green, good sir? Oh, because this is all of this is still green. Ah. Okay, why are you still green? Because we didn't connect you to the reset line, because I'm a dum-dum. You see, my friends, this is the kind of things that you will have to test out multiple times, because, yeah, there is just a few things that is going to be left on the table, so, yeah. It is a good idea to reset your memories, so, yeah, you want to have these memories reset by the same things that resets these memories, just for convenience's sake, because this will probably be all in the same vicinity, and as we can see, it got pretty much resetted, and now it's ready to roll again. Okay, I think this covers pretty much everything, my friends. Now, this is still developing tech. This is the most advanced one that I have yet built, the Infinite Encoder. It looks big, but it can be Tetrised out much, much better, okay? I do have the other showcase videos where we go through this design more Tetrised up. It's just that I don't want this video to be 4 hours long, while I'm just obsessively putting every single thing in its proper place. And what... Oh, yeah, this thing activated because, as you can see, like, this signal is still green, and, like, no difference happened to turn this off, and so the system activated itself again. So, yeah, my friends, I think this pretty much covers everything. I was as extensive as I possibly could, and I think I explained it in a reasonable fashion. There is pretty much, there is a lot of improvements that can be done to this, I'm certain, but right now this is the most advanced tech that we have so far. So, if you have still any questions, leave a comment below or drop by our Discord. You can also expose your questions there. This save file is going to be available there, as well with all the other save files for all the other tutorials are also there. So, yeah, my friends, like, subscribe, and leave me a comment, tell me that I'm a good boy. Bye-bye!